Hello students, welcome to lecture 41 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on fundamentals of hyperbolic metamaterials. So in this lecture, we will introduce you to hyperbolic metamaterials, discuss about the physics behind multi-layered hyperbolic metamaterials and some of their basic properties. We will consider these two geometries of hyperbolic metamaterials. The first one will be metal wire arrayed structure, then the second one will be multi-layer metal dielectric stack structure. After that, we will discuss some applications of hyperbolic metamaterials. So, hyperbolic metamaterials, these are highly anisotropic, uniaxial, sub-wavelength artificial nanostructures material that has got hyperbolic dispersion. So, if you look into their dispersion diagram, that looks like a hyperbola, right. So, what is so unique with this metamaterial? They basically act like metal in one direction and like a dielectric in the two orthogonal directions. So, normally you will see that all natural materials or even like the other metamaterials that we have designed till now, they have the same sign for electric permittivity and permeability tensor, okay. But in hyperbolic dispersion, you will see that the principal components of permittivity and permeability tensors have different signs. So, the origin and the purpose of this is that it was initially developed to overcome the diffraction limit of optical imaging, and we will discuss how it works in this particular lecture. So, this hyperbolic metamaterials basically possess a broadband singularity in the density of photonic states. Now, when I talk about broadband singularity in the density of photonic states, it basically refers to a unique property of some metamaterials where the density of states for light waves or photon is significantly enhanced over a wide range of frequencies. This singularity leads to unusual behavior in how light is going to interact with this kind of material that basically influences the phenomena like spontaneous emission and light propagation. So, if you consider this photonic density of states, that is basically describes how many different light wave states exist in a given energy or frequency. And when we talk about singularity, in the context of photonic density of states, a singularity basically means a large or infinite value at a specific frequency or over a range of frequencies, right. So, here we are talking about broadband singularity. So, broadband means the singularity basically occurs over a wide range of frequencies, not just a single point. Now, what are these materials with hyperbolic dispersion? So, these materials are basically, as I mentioned, they are artificial nanostructures or engineered structures. Need not be nanostructures. Nanostructures we continuously keep on telling because in the context of optical metamaterial aspect, if it is in microwave range, the dimensions are typically in the millimeter range, right. So, these metamaterials are basically artificially engineered structures that can exhibit unique electromagnetic properties which are not found in nature. We all know this, right. So, one such property is this hyperbolic dispersion, where the dielectric permittivity has got different signs along different direction. That means, say your epsilon parallel is positive and epsilon perpendicular is negative, right. So, this kind of different signs basically lead to broadband singularity in the photonic density of states. Now, what is the consequence of this? Okay, this thing is basically interesting because it can enhance the spontaneous emission. So, light sources kept near this kind of materials may emit light much faster, that is it can shorten the spontaneous emission lifetime, okay, and it can also modify the light propagation. So, light can actually propagate in a very unusual way, including supporting very large wave vectors due to the large number of available states. So, what are the applications of this kind of hyperbolic metamaterials? These properties are basically explored for applications in the areas of single photon sources, quantum communication and sensing, right, etc. So, in essence, you will see that metamaterials with hyperbolic dispersion basically offers a way to control and manipulate light matter interaction in a way which is not possible with the conventional materials, right. So, it gives you very unique features. Okay. So, what are the typical material types that can show this kind of feature? The first thing is, it was initially believed that it is only achievable through artificial structures. Okay. Later it was seen that some natural materials within some specific frequency range can also show this kind of properties. Even physical vacuum may exhibit hyperbolic properties under strong magnetic fields. So, here you can see the 2D dispersion relation that connects momentum. Okay. So, this is basically the dispersion relation of air and quartz. Okay. So, this is the K-space diagram. So, this particular rings are basically telling you about the permittivity or the refractive index. Okay. So, this value is basically, because this is in K space, so you are writing everything in terms of the wave vector K. So, this is in air you have K naught, and in quartz you will have 1.45 times K naught. Okay. This is the wave vector. So, this is the typical dispersion relation of air and quartz in this particular K space, right. Now, there are some materials that also shows elliptical dispersion relation, which can be found in anisotropic medium. So, here you can see that this is the circular one is shown for air, and this elliptical one is for some anisotropic material, right. And finally, on the third figure you can see something that is called hyperbolic dispersion, where the dispersion diagram looks like hyperbola. Okay. So, in the K space, which is basically marking your Kx and Kz, you can see these are the dispersion curves. Now, these contours are also special contours. Okay. So, here what happens, these are called isofrequency contours. Okay. Or you can also call them equal frequency contour, that is basically a graphical representation in the momentum space or the K space that shows all the possible wave vector corresponding to a particular frequency or energy, right. So, it is basically a critical tool that allows you to understand the wave behavior, particularly in periodic mediums like photonic crystals and solids. Okay. So, the shape of the isofrequency contour basically reveals whether the material is isotropic or anisotropic, right. It basically tells you about the wave propagation direction and the potential of some exotic phenomena like negative refraction and all, right. So, you can see that these isofrequency contours are basically plotted in momentum space or K space. So, each point is basically giving you a value of K, that is a wave vector. Okay. And in a particular contour, all the wave vectors are having the same frequency, that is why they are called isofrequency. Okay. So, typically they are used in photonic crystals, where this kind of isofrequency contours help us to analyze how light is going to propagate through this structure. So, if you see a circular contour, that basically tells you isotropic propagation. Okay. And if you see something like a square or a star shape kind of isofrequency contour, that will basically give you anisotropic behavior and some new properties like self collimation or super prism effect. Okay. You can also see negative refraction from isofrequency contour. Okay. So, you can use that for seeing whether the light wave is bending in the other direction or not. So, those things you can see in more details for the isofrequency contour in the case of photonic crystals, right. So, here what is more interesting, why we are showing this isofrequency contour in the case of hyperbola or hyperbolic metamaterial is that here you see that they can extend up to very large values of wave vector. Okay. And the pointing vector is basically normal to the wave vector, right. And this is basically for reference, it shows you what is the wave vector in air medium, right. Now, here we are plotting it for a natural material which is isotropic. So, in this case we consider epsilon parallel and perpendicular to be equal and both are positive. So, in that case the K space diagram, okay, looks like a spherical shape one in 3D. You can see here in the previous case we are basically taking the cross section of the 2D in the xz plane, and that is why we were seeing that circle. So, it is basically the xz plane. So, in 3D it looks like this. Now, if you have a medium that is anisotropic, that means the values are both positive, but yet they are not equal. So, in that case you will get a ellipsoid kind of isofrequency, or you can say this is the dispersion relation that gives you this kind of a ellipsoid. Okay. So, you can see in the K, in the xz you can get this kind of ellipsoid kind of isofrequency contour. So, this basically tells you about the anisotropy in the medium. Now, these two figures C and D, they are basically telling you about the hyperbolic dispersion relation, because here you see the parallel and the perpendicular component of the permittivity, they are unequal and they are also of opposite sign. So, if perpendicular epsilon perpendicular is positive, you get this kind of a dispersion diagram, and if the parallel part is positive and the orthogonal part is negative, you get this as your dispersion diagram, right, in K space. So, you can understand that the electromagnetic properties of this kind of hyperbolic materials can be analyzed using non-magnetic uniaxial anisotropic material, and till now we have seen that dielectric permittivities typically along the x and y direction are considered to be epsilon parallel, and along the z direction we consider it to be epsilon perpendicular, right. So, this is what you can also apply here for the case of say some multilayer hyperbolic metamaterial. You can use this kind of convention, right. So, what will happen in this kind of a material when it interacts with electromagnetic field? You will see that the electromagnetic field can be decomposed into ordinary wave and extraordinary wave. Okay. So, you will see in one case you will find no Ez component, in other case you will find a non-zero Ez component, right. So, let us define a scalar extraordinary wave function which is phi equals Ez, and this basically isolates the extraordinary wave component. Now, after applying Maxwell's equation in the frequency domain, you will see that this phi basically leads to a wave function for phi omega, assuming that this parallel and the perpendicular component of the permittivity, or you can say parallel and perpendicular permittivity are basically constant within the material. So, you can basically think of this is the isotropic case and this is the anisotropic case. You can consider this one. Okay. So, you can write omega square by c square phi omega equals minus dou square phi omega by epsilon parallel dou square dou z square minus 1 by epsilon perpendicular dou square dou omega. So, this will be omega, okay, dou x square, same thing you can take here, it is a typo, okay, plus dou square phi omega dou y square. Now, in the case of an ordinary elliptical anisotropic medium, you will see this is the case that where both epsilon parallel and epsilon perpendicular are basically positive. But in the case of hyperbolic metamaterial, these two will have opposite sign. So, for extraordinary wave in an usual uniaxial dielectric material, the dispersion law can be simply written as kx square plus ky square divided by epsilon perpendicular plus kz square divided by epsilon parallel will be equal to omega square by c square. Okay. So, this basically defines the ellipsoid in the momentum space or the K space. Now, if you put in this equation epsilon perpendicular equals epsilon parallel, you will basically get this as a sphere, and that is the case in a isotropic medium. Now, based on the sign and amplitude of this epsilon perpendicular and parallel and perpendicular, you can have some major differences. The first thing is the dispersion shape. For elliptic media, the dispersion relation basically forms a ellipsoid in the K space. Now, if you consider the two components epsilon parallel and perpendicular to be equal, this ellipsoid will become a sphere. That means it becomes a isotropic media. Now, in the case of hyperbolic media, one component is negative. So, in that case the dispersion becomes a hyperboloid. Okay. So, what happens to the wave vector? So, in elliptical media you will see that the K vector magnitude are basically finite, which limits the resolution, and that brings that diffraction limit. But in the case of hyperbolic media, because these are hyperbola, there are no limit on the K vector magnitude. That means K can be very large, that means lambda can be very small, that means it can support super resolution imaging. Now, in the aspect of photonic density of states, we have already briefly discussed. In the case of elliptical media, it has got finite phase space volume between equifrequency surfaces. So, you have finite density of states, but in the case of hyperbolic media, you have infinite space phase volume because of the hyperbola. So, you have infinite density of states for each frequency, where the two permittivities are basically having different signs. Now, how they are robust to disorder? So, even with disorder that modifies the permittivity values, you will see that the hyperbolic shape still persists. That means it can still preserve the infinite density of state, and this is one of the main reason why this hyperbolic metamaterials performance are very strong and robust. Okay. You can also use effective medium theory for describing this hyperbolic metamaterial. However, there is a range of validity. So, you will see that effective medium approximation basically breaks down when the wavelength of the propagating mode is becoming comparable to the size of the unit cell. Okay. So, you can actually introduce a natural wave vector cutoff. You can consider K max to be 1 by A. So, this unit cell size A in metamaterial typically varies with the design. Normally, we will see that A is in the order of nanometer. So, the hyperbolic enhancement factor in the optical density of states will scale as rho omega, which is rho naught omega K max divided by omega by C whole cube. So, you will see this term rho naught omega is basically proportional to, or it's almost equal to omega square, that is the density of state in free space, and then you have K max, which is basically 1 by A, that is the wave vector cutoff due to the finite unit cell size. From that you can obtain what is the typical optical density of states. So, what you see that even with this particular cutoff in place, the hyperbolic singularity yields density of states enhancement factor of around, because there is a Q factor over here. So, it is 10 to the power 3 to 10 to the power 5. So, it is pretty large, right. So, with that, now let us look into the physics of multilayered hyperbolic metamaterials. So, first thing, the optical response of a hyperbolic metamaterial can be predicted using effective medium theory. Okay, and this works because the hyperbolic metamaterial components are typically deeply subwavelength in size. Okay. So, effective medium theory can provide you very useful information. However, it does not account for the strong non-local effects that takes place within the structures. However, within this kind of limitations also, okay, you will see that effective medium theory can capture the key features of wave propagation inside hyperbolic metamaterials. So, here is a picture of a typical hyperbolic metamaterial, which is formed by the stacking of metal dielectric layers, okay, into a 1D subwavelength crystal. So, the yellow one shows metal, the lighter color shows dielectric, and then you are basically repeating. So, you have epsilon d and epsilon m as the permittivities. So, this is x, y and z direction. So, x and y, these are the parallel direction. So, you have epsilon parallel and z is the perpendicular direction, considered as epsilon perpendicular. So obviously this crystal brings artificial birefringence, okay, and the extraordinary, you can see the optical axis is basically perpendicular to the surface plane, it is along the z axis, and the optical response in plane will basically differ from that in the bulk. And according to the effective medium theory, okay, you can calculate the components epsilon parallel and epsilon perpendicular using simple boundary conditions, right. So let us see how it is done. So let us first consider an electric field which is polarized along the surface plane, okay. So the wave is falling from the top, okay, and the electric field is polarized along the surface plane. So in this case the field is continuous at the metal dielectric interface. So you can write EM equals ED equals E effective. So M and D are basically metal and dielectric, and effective stands for, F stands for effective here, okay. The field is continuous, so what you can do, the effective, you can see what will be the effective electric flux, that is basically the sum of the flux densities in the metal and the dielectric. So you can write D effective parallel will be epsilon parallel E effective, right, and that can be written as Fm dm plus Fd dd. So Fm and Fd are basically the volume fraction of the metal and the dielectric. So obviously if you calculate one, the other one will be, so Fd will be 1 minus Fm, like very simple. But typically it is given like this, that Fi or Fj will be simply Tj divided by T tot. So Tj is basically the thickness of the jth material and T tot is the total thickness of the unit cell. So here the unit cell is basically one metal layer plus one dielectric layer thickness, that is the unit cell. So now you substitute this equation 1 into equation 2 and you can see how this looks like. So you are basically having epsilon parallel, which is given as epsilon d Td plus epsilon m Tm divided by the total thickness Td plus Tm, right. So that is how you can obtain the parallel permittivity. Now let us look into how we can calculate this epsilon perpendicular. So in this case we have to consider electromagnetic field that is polarized perpendicularly to the HMM surface plane, that is electric field is along this direction, to be honest, okay. And in this case the electric flux dj is considered to be continuous across the interface, okay. In the previous case the field was continuous, here the electric flux is continuous. So you have D effective can be written as dm equals dd, and from that you can write D effective perpendicular will be equal to epsilon perpendicular E effective, and that will be nothing but dm plus dd, right. So the effective field in this case can be expressed as a volume fraction, the averaged as E effective will be nothing but Fm Em plus Fd Ed. So once you substitute this into this equation, you can obtain what is the formula for epsilon perpendicular, and that turns out to be epsilon perpendicular should be equal to Fm by epsilon m plus Fd by epsilon d inverse. So once you do this calculation, you will get epsilon m epsilon d times the total thickness, that is a period, okay, Td plus Tm divided by epsilon m Td plus epsilon d Tm. So that is how you can obtain the perpendicular polarizability. So now we know how to calculate epsilon perpendicular and epsilon parallel for this kind of materials. With that, now let us look into two geometries of hyperbolic metamaterials and estimate these parameters, okay. So let us consider the first one, which is metal wire array structured hyperbolic metamaterials. So you can see it is basically hyperbolic metamaterials made of metallic nanowire arrays. So these are parallel metallic wires embedded in a dielectric matrix, okay. You can see the parameters shown here, the periodicity is A, okay. This is the z axis, this is x and y. So metal has got epsilon m permittivity, dielectric has got epsilon d, right. So we consider that the period, that is A, is much smaller than the working wavelength. So in that case you can consider this structure as a homogeneous uniaxial isotropic medium, right. So, you can consider epsilon z or epsilon parallel as the permittivity parallel to the wear, and then you can consider epsilon x and epsilon y, which will be equal to epsilon perpendicular, because that is perpendicular to the wear axis. So, this behavior you can model safely using the effective medium approximation, because the period is much smaller than wavelength, right. So, how do you do that? You can use the formula like this. So, epsilon perpendicular, which is epsilon x and epsilon y, will be p epsilon m plus 1 minus p epsilon d. So, p is basically the volume fraction of the metal wear in this material, and epsilon parallel, that will be equal to epsilon z, will be simply epsilon m epsilon d divided by 1 minus p epsilon m plus p epsilon d. So, this way you can very easily find out the perpendicular and parallel permittivities, right. So, you will see that epsilon m here, because it is metallic, so epsilon m is basically negative, epsilon d is positive, right. So, you can consider silver and aluminum oxide for this kind of a system. So, and you can consider p to be 0.5. So, in that case you will see that epsilon perpendicular becomes negative, and epsilon parallel, which is along the wear, okay, that remains positive across a broad spectrum ranging from visible to NIR. So, that is basically giving you a hyperbolic isofrequency contour, and that can also enable negative refraction. So, negative refraction, why we say it like that? Because at any point if you take the normal on that hyperbola, that will basically give you the direction of the energy flow or the Poynting vector. So, you can do that and see that it basically goes in the opposite direction as from the conventional material. So, you will get basically negative refraction. So, this kind of nanowire method that supports negative refraction because of the hyperbolic dispersion coming from its deeply curved isofrequency contours, and that basically enables the Poynting vector to deviate negatively, that means in the opposite side, and that is applicable for many applications. However, if you see the practicality of this kind of a structure, fabrication remains very challenging, and that is why people have opted to a much simpler design, which is a metal dielectric multilayer stack, okay, that we have just seen in the earlier figure, and that offers a much more practical solution. Okay, so here is a picture of how this multilayer stack looks like. So, it works on the same principle, and you can use effective medium theory as long as this periodicity is much smaller than the wavelength, and the material selection can be tuned to desired operating wavelength. So, you can actually use silver plus aluminum oxide, which is typically suitable for ultraviolet, visible and infrared. Okay, you will see different type of other materials like zinc oxide and indium tin oxide also people are using. Okay. Here the fabrication is easier because multilayer fabrication will be comparatively easier to implement if the layers are smooth and thin. And one thing to remember, that the layers must be very thin compared to the wavelength, so that you can use the effective medium theory to understand its behavior. So, what do we require? We require thin layers, but then if you make them too thin, they may lose their bulk properties, and that is why to maintain the precision in the fabrication is very important. So, here are some key applications of hyperbolic metamaterials. The first one is that it allows to break the diffraction limit of light and allows you super resolution imaging. You can use them for enhanced quantum electrodynamic effect. You can use them for stealth application. They can be used for thermal hyperconductivity. Okay. It can also contribute to research on high temperature superconductivity. Okay. Other applications could be like spontaneous emission enhancement, ultra fast light sources. You can see hyperbolic metamaterials over here. You can also use them for unidirectional transport or second harmonic generation. Okay. So, here are some key applications for which hyperbolic metamaterials are very popular. First one is super resolution imaging or hyperlens. So, the application enables imaging beyond the diffraction limit, allowing visualization of nanoscale features with high precision. So, you can see that hyperlens can basically transform the evanescent waves into propagating waves to produce images with subwavelength resolution, right. Here you can see that, and that is because the hyperbolic metamaterials can support large wave vector modes. Okay. You will also see that they support enhanced spontaneous emission, that is Purcell-Effect. Okay. So, they can increase the local photonic density of states, okay, and that will allow you to enhance the emission rate of light from emitters such as quantum dots, useful in LEDs, lasers and other quantum dot devices, quantum optic devices, right. So, that way quantum emitters which are embedded near the hyperbolic metamaterials show faster and brighter emission. Okay. You can also develop ultra fast light sources which enables the creation of high speed light emitting devices essential for fast communication and computing. So, you can see the figure here, okay, where on top of quantum well LED, okay, you have this kind of structures made of silicon and silver. Okay. So, these are those hyperbolic metamaterials being created. You can also think of negative refraction and flat lenses. These are used in flat lenses to focus light without a curvature, improving compact imaging applications. So, one example could be conceptual realization of Vizsgálógos lens with HMM. So, here in the figure you can see that lambda 1 wavelength just passes through, but lambda 2 wavelength is basically reflected. Okay. So, that is like you can see it bends light in a unusual way, showing the negative refraction. Okay. You can also see applications where HMMs can tailor the spectral and the spatial characteristics of thermal radiation. So, they can be used for thermal management in electronics, thermophotovoltaics and also near field heat transfer. So, these are some of the important applications where people use hyperbolic metamaterials. The last one is that not the last one, the couple of other applications you can say is the sub-wavelength sub-diffraction waveguides and interconnects. Typical applications in integrated optics where it allows light guidance into sub-wavelength regime, again because of the fact that it can support high K modes. So, you can also use them for nanoscale optical interconnects in microchips. Other application includes nonlinear optics where you can do frequency conversion like second harmonic generation, which are very useful in laser technology and telecommunication, and that can happen in metal dielectric hyperbolic metamaterials. You can also use metamaterials, this kind of metamaterials to band and guide light that can render objects invisible or make it less visible. That means you can do cloaking devices in microwave to visible spectrum. So, you can make cloaks for small objects using this kind of engineered hyperbolic metamaterials. And there is a compatibility of this kind of material to be fabricated on flexible and rollable substrate that makes them suitable for wearable and foldable photonic devices. So, with that we come to an end to this lecture. We will continue with the discussion of hyperbolic metamaterials again in the next lecture. If you have got any query, you can drop an email to this particular email address. Thank you.